Hi everyone. So in this video we'll discuss the main mechanism for computing the gradient in feedforward networks, which is called the backpropagation algorithm. And just note that there is a variant of this algorithm that's used for recurrent networks, for training recurrent networks, which is called backpropagation through time. We will get to that in the fifth and last section of this course. So basically, let's see where the problem comes from, right? So you have a feedforward network, you have an input vector x, and then that input propagates through the parameters of the network, so through each layer, right? So first it gets multiplied by the weights of the first layer, then you have the first hidden layer, then the first nonlinear activations, then it propagates through the parameters of the second layer, and so on, right? So it forward propagates through all these parameters. These parameters could be hundreds of thousands or sometimes even millions. And then you have a prediction, right? Let's call it y hat, a prediction of the label. Again, this is for simplification, a classification problem, but even in regression, you have a prediction of the value of the function that you're predicting, that you are learning, right? And then you apply the cost function based on the true label. This is the through training, right? So you have the cost that's a function of the true label and the predicted label. Now you want to compute the gradient of the cost so that you can optimize that cost function and minimize it and move the parameters in the direction that minimizes the cost. Now that gradient, right? So you want to compute the gradient of L of y and y hat with respect to theta. Now theta, as we said, can have hundreds of thousands of parameters. So it can have a very large number of parameters. So that's why we need an efficient way of computing the gradient rather than just computing the gradient with respect to each parameter independently. And what backpropagation does to reduce the gradient computation is basically it relies on finding common intermediate steps between the computation of the gradient with respect to different parameters. And to do that, right, so it relies on an abstract concept that we'll explain right now, which is called the computational graph. The computational graph is basically a graph whose every mathematical operation that happens in the forward propagation, right, is represented in the computational graph as a vertex, right? So for example, if I multiply two variables, then I have a vertex x1, x2. So I have x1 and x2, y could be equal to x1, x2. This is f1 of x, right? And then let's say I add a bias, that's a new vertex, z equal f2 of y. Maybe f2 of y is just y plus some constant, right? So the computational graph in general is a graph where a vertex is assigned to every new mathematical operation, right? And edges correspond to operands, right? So if I have a multiplication of three variables, then I would have three edges, right? But only one new vertex corresponding to the operation. So vertices correspond to operations, edges correspond to operands. Now, what backpropagation does is basically it relies on a very simple property of the derivative, or the gradient, remember, is just first order partial derivatives, right? So the derivative decomposes easily if I want to compute the derivative of one node in a computational graph with respect to a node that's not immediately connected to that node. So for example, here I want to compute the derivative of z with respect to x1. There is a very nice decomposition, is that the derivative of z with respect to x1 is the derivative of z with respect to y times the derivative of y with respect to x1, right? So in more like the justification of this, you can take it in a calculus course, but the intuition is very simple. Derivative basically is a computation of sensitivity. So the sensitivity of z, or the changes in z in correspondence to a small change in x1, can be computed as the change in z in correspondence to a small change in y times the sensitivity of y with respect to a small change in x1. So how much x1 will change in y, and then how much that change in y will cause a change in z, okay? Because there is no direct connection between x1 and z. Now, if I want to compute the derivative of z with respect to x2, I also have the derivative of z with respect to y times the derivative of y with respect to x2. Now, computing the derivative of z with respect to y is common between these two steps, right? And that's basically the basic idea behind backpropagation, is if you want to compute the derivative of z with respect to x1, and you know that you will also compute later the derivative of z with respect to x2, then store the value of the derivative of z with respect to y instead of recomputing it, right? So later we will discuss how like the computation memory trade-off, right? Whether you should recompute things or you should store them, right? So here we were discussing the basic backpropagation algorithm, which will always choose to store values instead of recomputing them. Now, beyond scalar values, so here this is scalar, so you have the derivative of z with respect to x1, the total derivative. If we go beyond scalars, then we compute the partial derivatives, right? So this is a slightly more complex computational graph, where you have x1 and x2 affecting y1 and y2 and then z. So x is a two-dimensional vector, y is a two-dimensional vector, and then you have z. Now, the partial derivative of z with respect to x1 is equal to the partial derivative of z with respect to y1 times the partial derivative of y1 with respect to x1, plus the partial derivative of z with respect to y2 plus times the partial derivative of y2 with respect to x1. Here, because there are two paths from x1 to z, one through y1 and one through y2. So to compute the sensitivity, the change in z as in correspondence to a change in x1, I want to know that change in x1, how much will it affect y1 and how much will it affect y2, and how much the change in y1 will affect the z and how much the change in y2 will affect z. Now, if we write this in matrix form, then the gradient of z with respect to x transpose, which is basically the partial derivative of z with respect to x1 and the partial derivative with respect to x2, is equal to the gradient of z with respect to y transpose times the Jacobian of y with respect to x. And Jacobian, it's a matrix now because y is multidimensional and x is multidimensional. So it has all the sensitivities of the y variables with respect to changes, small changes in the x variables. So here we notice that every step of backpropagation for one output unit, which is z here, right? So remember, you could have more than one output unit, involves the Jacobian gradient product. So here you have this gradient times a Jacobian. Now the computational complexity, if you notice, depends on the number of edges in the computational graph, right? So here, the computational complexity of computing the gradient of z with respect to x depends on the number of edges in that computational graph. Thank you.